Okay, so I'm going to do a quick overview of site-directed mutagenesis for sequence correction and plasmid modification, including what tools you need to use and how you need to use them. My name is Jacob Danielson. So why do we do it? Site-directed mutagenesis is a process where we can modify a DNA sequence to help us express a certain gene, or in the case of correcting improper ligation or improper PCR synthesis. But we can also use it to improve protein solubility by adding some cutting sites in, maybe adding like a GST tag, something like that. And then we can also modify the amino acid sequence for experimental investigation, such as testing important residues in like a catalytic triad and a protease, or some other features that might influence the folding or conformation of our protein. This can help us target ligand molecules and areas on the protein so that we can do drug design for protein structure rather than random or animal-based drug design. So what you're going to need is a mutagenesis system, as in a kit or a protocol. You can use protocols that don't require buying commercial kits, but kits tend to save time and reduce the amount of optimization needed for a particular mutagenesis, which can be very important in terms of saving time and money in the long run. So the other things you'll need is a primer calculator. These are typically included with mutagenesis systems or primer guidelines. This is more common in the protocol type situation. And then of course, a source DNA sequence, a target DNA sequence, and I like to use a program called a Plasmid editor, which is free, and then the NCBI BLAST. You can use this for DNA alignment and similarity, and for protein alignment and similarity. It would be very important when trying to identify the features you're trying to change in a particular sequence. There are 3 types of mutagenesis and then 2 implementations of the types. The types are insertion, deletions, and substitutions. 2 types are single and multi-site. So single site is typically a stretch of DNA that can be handled by 2 primers, or in the case of mutagenesis, you can sometimes use 1 primer, since we only need to amplify in one direction, because we're going to linearize the whole plasmid. And then multi-site typically refers to having multiple primer sets. So single site could actually modify multiple sites if they're close together, and multi-site can modify multiple sites that are farther apart, but you can most likely do multiple changes within the single primer. Where you run into problems is you have to have enough similarity that the primers are going to anneal to the source DNA. So you want to try to limit it to a couple of nucleotides that are spaced relatively far apart. And spacing in between those, you want to make sure you have stronger binding nucleotides. So if you can find an area, if the area you're modifying has lots of GC content, it's actually not a terrible thing as far as mutagenesis is concerned. It can still cause problems with the PCR step of mutagenesis. So, you know, template variety matters in all these things we do with DNA modification, genetic engineering, that kind of thing. So, but if the source gene you're looking at is 70% GC content, you just have to deal with that. Usually we're gonna add DMSO or maybe some kind of polyethylene glycol if it's suitable with a kit. Typically notes on that are on the manufacturer's website. So insertions are inserting a desired DNA sequence into the source DNA. This is effectively cutting and pasting in a particular sequence without modifying the things around it. Now, it should be remembered that inserting something, especially something that is longer than 3 nucleotides long, is going to cause frame shifting. This can be really bad if it goes wrong, because you could completely, you're not, when you go to purify a protein or express a gene, it's just not going to be the correct sequence, and most oftentimes leads to early or late stop codons and the entire changing of the amino acid sequence. So what I was saying is, it could be used for inserting restriction sites either at the beginning or end of a gene, so that we can use a bacterial vector to amplify the DNA, which is much more efficient than using PCR. And this can be important because sometimes you want a certain tag or a certain plasmid for expression in other systems, such as human or yeast expression. And the engineered vectors or plasmids typically have a certain cutting site arrangement. So it can be hard to natively find those things in the source DNA. So being able to add those in is a huge advantage of this technique. Adding in stop codons, so if you want to only express a certain part of a gene, especially for larger systems, such as super complexes and things like that, just to look at one functional group, that's useful. You can add in amino acids. This can be used to add affinity tags, which I've also added, but it can also be used to add, it just shifts everything over in the same reading frame. So if you think adding in a histidine or something at a certain location will affect the gene in some way, that'll help with solubility or affect function. And so we would do that for it. Typically, if we're looking at affecting function, we're going to use substitutions, but this depends. So with deletions, you can be used to move the reading frame. So if you ligated your DNA with a ligablunt in ligation, you had some erroneous insertions from that, this can be used to fix that. Of course, it's still not 100% efficient or successful, so you still have to do some sequencing, but it can be really beneficial to try and do this over trying to use a primer over the site and then try to religate it and re-express it. So it can also be used for removing early stop codons. Let's say the source DNA you get has the gene you want, but they've separated it into functional sites. You can use this to remove that to get 2 or more functional sites back together. And then use for removing amino acids, which may be important to, again, improve solubility or what have you. Substitutions are taking what's already there and adding some things in. These are typically easier to do because you're not inserting as much there. Because when we do like insertions and deletions, typically that has to be on the ends of the primers, which may not be suitable for that region. With substitutions, the primers are going to anneal most of the time. So we don't have to worry about as many problems as far as the PCR portion of the protocol. And it could also be used to remove restriction activity. Given that most amino acids have multiple codon coding codes, this can help with everything but methionine, as far as if you want to maintain the same sequence, but you want to remove restriction enzyme activity at a certain site, which can be important, again, for inserting it into a certain plasmid, or perhaps for removing some kind of endokinase site or something like that that might have been used in the past, but you don't need it at this point, and it might help with your downstream application. So how does mutagenesis work? First, we have our template DNA here, and we do PCR on that with the engineered primers, the specifications of the kit or the protocol, and then you're going to create a linear copy of the whole plasmid, but with your edit here on the left. And then we use DPN1, which is a 4 nucleotide recognition enzyme. So it cuts pretty much all templates. But the thing that's special about it is it's methylation sensitive. So if you use a DH5 alpha E. coli for the plasmid or vector expression, that is going to create a methylated DNA plasmid, and that can be cut up by DPN1. But when we use PCR, there is no methylation that occurs unless you add in a methyltransferase or something else, which could be used to selectively cut out things with DPN1. But you just got to make sure wherever you do that, you're going to have corresponding bands that allow for successful ligation. And then because it's cut up into so many pieces, the original template DNA is now gone. If you ligate too long, it may be able to reform into something, but most likely it's just going to reform into linear, non-circular DNA, which will then not be expressed in E. coli systems. One way you can look at the efficiency of a ligation is to use some kind of colorimetric expression site, such as a LAC-Z promoter, which will allow you to do like blue-white screening. That'll help reduce the amount of sequencing you have to do. However, if you have a good template and you have good primers, you most likely won't have to do too much of that screening because DPN1 is going to cut so much in the template DNA. Okay, that's it for that. So now we're gonna go get our tools. So I need target sequence. In this case, I'm doing an HIV-1 protease, which is part of another gene. So we're going to get the sequence. So FASTA, let's save it for right now. And then we're gonna go get the source DNA. So for this, we used a 21, PET 21A. HIV-1 protease and HIS6 should bring it up. Looks good to me. Let's make sure it's the right thing. So yeah, this looks right. 7600 BP. So we have ribosome binding site, protease. So from here, you download. Oh, I want to download that. Sequences. Okay. I'll just copy in. We'll just leave this up right now. And then a Plasmid editor. This is freeware. It just opens as an applet. So we're going to open this. And then once we save a file with this, run out of me. Maybe, there we go. You can donate if you like. It is a very useful tool. So, all right. Some features of this. This will tell you the starting nucleotide number for each line, and then this separates it into specific chunks of 10, but it does scale with the size of the monitor or window. And then this you can set whether your DNA is methylated or not. So in this case, we're gonna just say it's methylated, doesn't matter. And then linear or circular. This is gonna affect the digestion tool they have in the program. And then enzyme selector, so we'll be able to select any enzymes that we find useful. And then some save functions, finding functions. You can search by direct DNA. You can change the amount of mismatches. You can also search for an amino acid sequence, which can be really useful for finding landmarks in a plasmid. And then ORFs is the open reading frame. That's just going to look for the next ATG available. It's not looking for a ribosome binding site or anything. So it can be good if you know, oh, I have a histidine and then I have an open reading frame something like that. Or sorry, like a his tag. And then features allow you to annotate with color highlighting the sequence. So we're going to do a little bit of all that. Going to go here, copy all that. This program does not allow you to paste in fully ambiguous DNA. It has to be ATCG or N, and that's it, which can be really annoying if you want to find, if you want to do like a generic disambiguous DNA sequence, but not the end of the world. Okay, so we want to find our gene. So what we're going to do is, we already have it copied. I'm going to look up a translate tool. I usually use XPC, or however you say that. Okay, paste, translate. Oh, I forgot it does this. Let's do this. Let's, we'll need that later, so we'll leave that open. Last. So we're going to want to translate it. And then we want to align 2 or more sequences. And then, so this is our DNA sequence, and we're going to go to downloads, open the FASTA file. Oh, and then you want to open this in Notepad. You have a FASTA reader software, but typically this will work just fine. So it's now going to search the, that was quick. There you go. Now it tells us which bases line up the best with our enzyme here. So query 1 is the DNA, subject 1 is the amino acid sequence of what we want. So it's important to keep those 2 separate, that way you don't go the wrong way. Middle lane is the comparison. So if it puts a nucleotide there, that means it is the same. If it puts a plus, that means they are same in function. If there's a space, they're completely dissimilar. So those are major errors. Pluses are considered minor errors. So in this case, there's a leucine, an isoleucine, which basically they're the same molecular weight for the most part, and they're both nonpolar groups. So having that in there is not going to greatly affect the function of the protein, theoretically. Identities are the direct identity. Positives are things of similar function. So this is 95% similar in function, or the type of amino acid, and it is 93% similar in actual identity. So what this tells us is where we can look for our gene. So we're going to go from 3439 to 3735. You can also, because this sequence is correct, Control C, and then go here, Control F, Control V, and then grab the rest of it. Make sure you don't delete in the finding window. Control C, Control V. Get rid of those spaces. And then you want to align as amino acid. We also, if you want to see if the gene is in the correct, if the source DNA is in the correct orientation, you can remove this and it will not find the reverse complement of this gene. So there we go. It's not reverse complement. That's good. That means our source DNA is in the correct orientation. So now we're going to close this because you cannot modify the file while the find window is open. And then you go to new feature, use whatever color you like. I really don't like the blue. I like to go for a cooler blue. And this is our gene of interest. Okay, now that's saved. And for this, we're not going to worry too much about the rest of the sequence. We're just going to want to make sure the open reading frame is correct. So if we go to ORF and we go to find previous, it's your previous reading frame, or where this starts. So if you want to double check, you can put your cursor here, and this should be a P. This should be a Q. All right, so it's in line with this reading frame. If we wanted to go, if we look at the map of the enzyme of this guy, oh, I don't like this one. The other, there you go. So if you look here, ribosome binding site, so there's 2 binding sites here. So we should be able to, if we wanted to get rid of this and just use this vector, we can do that, but then we have to find a cutting site here and match it up with something down here. So right now we might do a case with NDE1. Let's see how that goes. So next thing you're gonna wanna do is you're gonna wanna open, oops, sorry. I wanna make a new thing. So this is gonna make it a lot easier to see what we're doing, less busy. And then I'm going to delete the feature. Ooh. I'm gonna click out, that's what I'm gonna do. Okay, so now we're gonna delete the feature. You could leave it there. I find it's better to start fresh. Save this as desktop. Say this is our HIV one. Copy X. Okay. Open our new folder. Save. I saved it as an 8 file. Can also probably save it as a text file. Oh, this is the HIV one. Oops. HIV one protease source. Okay. And now we're effectively done with that. This is going to be, I'm gonna say that as HIV1 protease. Gene interest. Okay, now we're going to modify this file to match the other file we would like. So there's this guy. Oh, we don't need that right now. So I can always open that up later. Where'd my black? Oh, open another. There we go. So we're going to go through this, and I like to go here. Be nice if it printed out what it says. I'm sure it's possible. I'm not aware. So the red spots here are differences between the 2 queries. So it should have, oh, let's see. Because one of these was, okay. So we're going to want to go back here. Then we're going to do a protein alignment. I'm going to be happier with that. Oops, one too many. Protein blast. So I do need that thing I just closed. Again, downloads. Okay, so I'm going to go, let's see. I want to align 2 more sequences. And we want this to be the subject because you just remember to keep them in order because you will have issues if you don't. And then we're going to use the XPC translate tool. That's not where I wanted that to happen. Translate. Very good. Okay, so now we're going to take our sequence from here, translate from 1. Again, it's going to do all the open reading frames. You don't need that. So you can just copy and paste here. Last. It should only take a second. And we want graphics. See, now there is a letter in here indicating which base is different. And then we're just going to double check to see which one is on top. Look here, we're after TLW, so TLWK. So this is, top one is what we want. This is what it is currently. So then what I do is I open an Excel sheet, which I don't have on this computer. File, spreadsheet. Looks all the same. Okay, and we're going to do a lot of manual counting. So we have what we have source, we have target. We're going to have position. This is the amino acid position, so we can do a insert position, nucleotide. Musician. I don't know what's going on with that. Okay, so this is going to help us find this. So first error is the source is Q. So I can, let's see if I can make this bigger. There we go. Oh, that's not what I wanted. How rude. Control minus. I don't understand how this is. Oh, okay. So now they're individually marked. And then I'll get the beginnings. Okay. So Q is 7. Source is Q. And we want K. Nucleotide, this is going to equal this times 3 minus 2. Insert one more. Position. T. So on the 3 end, this is on the 5 end. This is going to equal this plus 2. Okay, now I can use that for all of them. Next is 33 for L. So source is L. Target is I. This is just handy. I want to move it. Is it this? This move it? There we go. Okay, so we got 33, got 63, 67. This is L. I, C, A. Let's see what else we got. I think there's just 2 more, 3 more. 95. Oops. 5, 98, 99. Sure, I probably that's right. 6. This is C. This is A. This is K. L. And this is F. And then we'll just copy this. Let's mark positions from 0. So if you did this in the other window with the whole Plasmid, you would need to know where this started and then add that to this. So this is why I do it in a separate window. So we can search by a string. So we go here. You can search by these numbers. Here's another way to do it. So we know we want TLWK. It is possible there's more than one of those in the sequence, but it is something we can search for. So we just get rid of all this. TLW. Oh, in this case, it's Q. So the last 3 are going to be what we want to change. And there's no others. So close. Highlight that. Q feature. And we'll just change the feature to what we want. So we'll do K. Okay. We'll modify those as we go. So then search find. Next, we can do, we got a L here. So we can do TD, TD, L. Find next. Okay. So these last 3, you want to change to I. Feature, I. Okay. Let's see. Just keep doing this. Bear with me. QY. Q. I need new glasses. I. Next. New feature. Okay. Oh, that highlighting. Okay. Made a mistake there. I'm going to clear highlighting. There you go. So since we know this is L, I'm just going to tell you hit the next C. Likely the one we need to change. Feature, this needs to be an A. Okay. Last ones. Feature. Yeah. Okay. then 1, 2, 3, 1, 2, 3, 1, 2, 3, and A. Okay, so that's all the changes we need to make to correct the sequence. You can also add in, we want it to end the enzyme here. So we're gonna put in TAG. That's gonna help ensure that the enzyme stops. Where'd that go? Oh, that's so annoying. I did something and I don't know what. I don't want this. Okay, whatever. I don't want to hide anything. I'll have to go away. Check that. I don't know why it does that. Okay. Okay, so next thing to do is we probably want a cutting site here. So let's look at the so we look at source DNA. Oh, I don't have it up. Go to blind. Oh, I don't use that. Ah. Okay, now it'll be easier to find that. Or why it always does this. Open with another app. Turn on the PC, desktop. Beep. Okay. Oh, I'm gonna lose my mind. No, I don't. Open it with whatever this thing is. Open with, choose another app. This guy. Okay. Okay. Open. No. Oh my gosh. Right on this guy. Oh, this is this with apes. There we go. I don't have to worry about that anymore. Troubleshooting on the fly. I love it. So I want to find this tag. Should be 6 H's. One more. Find next. One, two, three, four, five, six, eight, 1 too many. There we go. So if we want to close the gap here, what's this? All right. So we're looking for something between 31.95 and 34.38 enzymes. That's what I mean by you can't edit anything. Okay, so enzymes, enzyme selector, unique. We're just gonna select this guy. So we want 319. Just like this. We'll do 319 to 34 something. So this is a possibility. This is a possibility. This is going to cut out more junk. So what we can do is we'll just excuse me. We'll just use NSI1. So that would be ATGCAT. So nice thing about that it really matters. ATG right? ATGCAT. I don't know what this is. So annoying. I feel like it's some kind of inspection tool. No, I don't want that. That's one thing about this program. There are a lot of hotkeys, and I don't necessarily know what all of them are. That's what it was. I hit space. So there we go. Seems like an odd place to put a hotkey. Okay, so this is one change I want, is the NSI tag. And then I want to go through and correct all these. So remember, we're on gene of interest right now. I guess I should change the name of that once I go to do it. But we're going to save what we want our thing to be. So our first feature, I'm going to go here. And then we're going to sort it by location. That way they're in order. Okay, so the first one is here. K. So currently it's CAA and we want K. We're gonna go here. Look up a codon chart. Edges. And seems like guy has the single letter abbreviations. See if I can make it bigger. Some kind of menu blocking that, and then we'll move this over here. Okay, so we have CAA, but we want K. So go over here, look around for K, lysine. The easiest thing to do is to just change this to an A. We're going to do that with a lowercase letter. Next, we have I. We want an I. I can be AU anything. So right now we have TTA, which is not the same at all. I guess we could do this. ATA. Very good. And then here we have I, CTC, which is not what we want. Oh, yeah. What? One I here. CTC. Oh, so we just need to change the first A. And then we want A here. So look for A. Alanine, where are you? There you are. So GC anything. So change the first two to GC. Next, TGC here. We want A, alanine again. That could be GC anything, so we're just going to do GC. And then here in we want, which is, where you at? There you are. So AAU, or AA something, AG. So we just need to change this to a C. Good. You could also do AAT. Can help reduce issues with improper annealing. What's next? CTT. And we want F. We don't know. There it is. TTT. So we can change this to a T. Perfect. Add a feature of F. This one thing, I don't know how to change this. Okay. Some kind of computer error. There we go. I didn't like that I was in window mode. So, and then we want to change these to lowercase. Edit to lowercase. So we want everything in lowercase to be things we edited. And then next, we're going to take our code and we're going to check to see if we got all of our changes correct. Let's see here. So this is our inquiry. We want to edit the search. Remember which one is the one you want to edit. So this one is our, oh, probably gonna yell at me. Yep. Okay, so we want blast X. There you go, blast. 100%. The identities are 100% and the positives are 100%. So now we have, this is the correct sequence, except for we added some stop codons here. And, and this cutting site as I want. So we might want to do feature and NSI1. Sure. And then feature stop. Okay. So now, file, I'm going to save this as gene of interest. target. And then we're going to go back to this. Modified this so it's a source. We don't get confused. Okay, so now we want to open this guy. Oh, already open. And we have our section here of the thing we want, or the gene of interest without the addition. So now we're going to take this, copy it into that hole. And this can be useful if you want to do some digestion analysis and stuff like that. So we're just going to save it as protease. Target. Very good. Okay, so now we are going to be using the Q5 mutagenesis system. So go ahead and set that up. And NAB is awesome. They give you lots of interesting information on how and why it works, and also a very easy to use tool. So we want to close this and this, and even that. And we want to open source target. Going to help us stay organized. So you want this whole thing. This tool also helps you detect whether your sequence is too long or things like that. We're going to call this HIV1 source. You have to give it a name. And then our start, we're going to do both of these guys up. So we're going to inspect what we're really wanting to do here. So we're wanting to insert here this cutting site. So we can look at how long this is. We may be able to do two things at once. How long is that? 27. That is very doable. So we can save that. And then we have to note where this is happening. So they want you to put this is an insertion. The way we would be doing this would be an insertion, because we want to, theoretically, you would do one insertion for this object here, this cutting site, and you would do one substitution here with this lowercase a. And we can save doing two steps by just doing one insertion. So it's effectively just going to put the same thing there that we already have there for most of that sequence, but because it's short enough, we can just do the one insertion. That'll save us a step. So we go to insertion, make the desired sequence. And then if I remember correctly, they want this letter here, its position. So the start is 3, 4, 3, 8. And the end is just after this, 3, 4, 3, 8, and 3, 4, 6, 6. So 3, 4, 3, 8, and 3, 4, 6, 6. Okay, and we're not adding any tags here. You could add in histidine, what have you, but don't worry about it. It is now. So, oh, I guess I didn't save my sequence. Well. So this is our starting sequence. We'll recopy that. Hopefully, it's probably going to make me put the thing back in again. Continue. Yeah, save it. Okay. We want insertion. And we want from here to here. I know. 8, 3, 4, 6. Okay. And now it has a reading, 3 reading frames, and your primers. But because I know everything's in the correct reading frame, I don't really have to worry about it. You can always double check. You can see we're in reading frame 1, which is good. That's where we should be, since I put it in base order. As then this is every base has 3 complements and it's going in the right. We're not inserting an odd number of bases. And by odd, I mean 1 or 2, not literally odd. So what we should see here is this last base is changed to an I, which is good. And we should see these 2 bases here, which is not that important, but it is correct as in but we want to add this ATG cat here. So, oh, I'm sorry. This is part of the vector. So ATG. So we want this MH. Okay. And then they give you your primers here. So you would write these down. What's really nice is they typically give you something that's very close in TM. You can see they're different by 1 length. They give you a good GC percentage. This is wonderful. It's really great. So you would want to record both of these primers, and then that would be your first step. So since we already have the sequence loaded, we're going to go ahead and do an insertion, or sorry, substitution. So let's see, we want this. So I don't have to copy and paste that, but we do need to know the position. So 7608 and, oh, my bad, 3541 and 3543. 3541. 35, 43. This thing is so picky about what you put in here. So we want ATA. What are you talking about? Substitution. 3541. ATA. Awesome. Okay. So as you can see, we have our sequence here. The only thing it could be, because otherwise, so the modification's happening here. So if we go back to, not that one, I guess that works. So we know this is the 3 bases. So we can grab, there you go. So it should be DTVI. So if we go down here, DTVL, that's exactly the change we wanted to make. Right. Oh no. Why? Oh, I. Yes, that's. Oh boy. Looks like we were off by something. I was a little bit before. Correct. APA, yes. No. There it marks it. We're changing GAA. Which GAA is what? E. Seem right. I don't know what this is. Yeah, it's the changes we want. Okay, I don't know. For some reason I'm out of it. Looking out too many letters. ADD, ADD, TVL. Why is it called though? Let's go from here. why we always double check the computers. So ADD. Oh. Ah, I see the issue. Okay. So the reason is this has my tag included here. So I need to subtract 6 from each one of these. So we can do 1, 2, 3. Great. Okay. So let's just delete this real quick. No, we can just do it Control Z, get that back. So 3, 5, 3, 7, 3, 5, 3, 5. Alpha. Well, repeating digits. 3, 5, 3, 5, 3, 5, 3, 7. ETA. There we go. This should be correct. ADD, TDI. So we go here and we grab the 3 in front and then back it up some. DTDIE. That is exactly what we want. Beautiful. So then we would take these primers here. Look how nice this is. They get the GC content right. They get the annealing temp right. Very specific. Easy to do. And they even give you a nice little name. You can put and just copy that right into urethans or your oligonucleotide synthesizer, whoever that is. Okay, so that's a. Oh, here we go. So this is an insertion. You can see they change a little bit. That's because this would have 2. This would not have 2. Or no, yeah. So substitution, insertion would just, I don't know. I could just delete it, but whatever. But yeah, substitution. We don't have any evolutions to do. But theoretically, say we wanted to walk this back here. Let's say we want to get rid of F. So we want to look at where these are at, because we don't really care for deletion. You won't have to put in what you want. You see, it's just the position. So if you wanted to delete this base, F, excuse me, you would just type in the distance you want deleted. So 3733 and 2 after 3733 and 3735. So it's going to cut out the CTT, which here was TTT, but that's because we had modified this in the previous step. So this is just going to kneel basically around, just it's going to read this way, and then it's going to read this way. And then when you recircularize, that section's not there. Very nice. Which looks like is what it does. So yeah, it goes ATG, whatever, that way, and then GAG, CT, reverse complement. So yeah, CTT, GAA, whatever. So reverse complement of that direction. So it's just gonna skip those 3 bases. Okay, so no, I don't want to save those changes I made. So once you got your primers, you would then order them and use the protocol here for mutagenesis, and they give you lots of information on how to do it. And little notes. Yeah, so that's it. Thanks for watching. I turn off the recording.